Hey folks, how you doing? We're starting section 2.4 today on linear independence. Let's go ahead and get started. We have been talking about, we started talking about this last time, two questions about linear combinations. One of the questions is, if we have a set of vectors and another vector b, is this vector a linear combination of the vectors that are in the set? Can I put weights on each of these two vectors so that when they add up together, they add up to b? Is that even possible? Um, and the um, and we talked about this in the last video. We said came up with this definition that the answer is that this is possible if B is in the span of S. Today we're going to look at this question. If we have a vector that's B, is it possible to construct B as a linear combination in more than one way? When we try to make this construction, will we have a free variable? Is there a way that we can tell without it just actually having to go through and solve the problem? So, all right. So as I mentioned already, we have answered the first question. The vector B is in the span of S, if and only if it's possible to construct B as a linear combination of S. This just says it's possible. It doesn't say it's only one way or more than one way. We don't know how many ways, but we do know that it's possible. And that means if we put the vectors in S on the left side of an augmented matrix and a B on the right side, the echelon form will not have a leading entry in the augmented column. So we have seen this already. Before we get into answering the second question, I want to mention one more thing. Actually, two more things. We say that the set S spans Rn if it's possible to construct every vector in Rn as a linear combination of S. In other words, if all vectors are possible, then the S spans the entirety of Rn. All of the n-dimensional vectors are part of the span of S. That's not always true. Sometimes S just spans a plane within three-dimensional space, for example. But if every vector is possible, then S spans Rn. And this means that if we put the vectors in S into a coefficient matrix with no augmented column, so these are the vectors that are in S, then the echelon form will have a leading entry in every single row. Because then no matter what we augment with, I can't have a leading entry in the augmented column because all of the leading entries are already accounted for. So a way of telling if every vector is possible as part of a span is to test if the leading entries are in every row. Okay? And now the other thing is that the zero vector is always a linear combination, no matter what set you're looking for, because no matter what your vectors are, if I assign the weight 0 to every vector and add them together, the answer will be the zero vector. So there's always at least one vector that is possible as a combination, and there can be, could be as many as all of the vectors, but the zero vector is always possible. Okay, so let's move on. Today we're going to look at a concept that addresses the second question. How can we tell if a vector is a linear combination in more than one way? We're going to have a definition. We have a set of vectors. We say that the set S is linearly dependent. If the vector 0, if the zero vector, and we know that the zero vector is always a linear combination, if that vector is a linear combination in more than one way, then we set this set as linearly independent. So just summarizing a little bit, the zero vector is always a linear combination in this way. 0 is equal to 0 times v1 plus 0 times v2 plus up through 0 times vn. If there is another combination that adds up to 0, then we say that the set v1 through vn is linearly dependent. All right. So, and vice versa. If not, we say that the set v1 through vn is linearly independent. So, all right. So let's see an example. I have these 3 vectors here. And this combination adds up to 0. If I take this vector and weight it by a factor of 2, and this vector and weight it by a factor of -1, and this vector and weight it by a factor of -1, that combination adds up to 0. 2 minus 2 plus 0 is 0. 2 again minus 1 minus 1 is 0. And then this is going to be 0 plus 1, because it's -1 times -1, and minus 1, because it's -1 times +1. That combination adds up to 0. And now we have a second combination that adds up to 0. And so this set of vectors, v1, v2, and v3, is a linearly dependent set. So let's look at this set. Can we show that this set is linearly dependent? So I'm going to rearrange this slide to give myself some way to work. Put the problem up here. And we want to show that this set is linearly dependent. So I'm going to put these vectors into a matrix. And I'm going to augment it with all zeros. But as we'll see in a little while, augmenting with zeros isn't really necessary, but I'm going to go ahead and do that for this example. And we're going to go ahead and put this into echelon form. So I want to change this -4. So we're going to take 4 times row 1 and add it to row 2. And that's going to give me 1520. 4 and -4 cancels. 20 and 0 is 20. And 8 and 2 is 10. And then the bottom row is 0, 2, 1, 0. And now we need to change this 2 into a 0. And so we're going to take 10 times row 3 minus row 2. So the 2 and the 20 will cancel. And you can see what's about to happen. 20 minus 20 is 0, and 10 minus 10 is 0. And now we have a free column. And that means that this equation has more than one solution, this system of equations. That means there is more than one linear combination that adds up to 0. Because I've augmented with zeros, I row reduced, we got a free variable. And when we have a free variable, that variable can be any number, which means we have more than one solution. It doesn't have to be 0. So there's more than one linear combination that adds up to 0. And by definition, that means that the set S is linearly dependent. And that's what we wanted to show. All right. I mentioned a moment ago that it's not really necessary to augment with zeros because we have a theorem that says if I have a set of vectors that's linearly dependent, then not only is the 0 vector possible in more than one way, but every vector in span of S is a linear combination in more than one way. It doesn't really matter what we augment with. We will always get that free variable. So let me take a look at this example here. And it's going to depend on the result that we just saw before. So I'm going to go back to the previous example, and then we're going to move forward in a moment, okay? So I'm backing up here. We know that this set is linearly dependent, but let's keep going. I'm going to put this into reduced echelon form now. This is echelon form. To put into reduced echelon form, I want to change this 20 into a 1. So I'm going to take row 2 divided by 20. 0, 2, 1, 0, 0, 0, 0, 0. There's my leading entries. Now I want to cancel this 5. So I'm going to take 2 times row 5 minus 5 times row 2. That's going to temporarily mess up the 1, but we can fix that later. So 2 times row 1 minus 5 times row 2. So that's going to change this to a 2. And then 10 minus 10 is going to be 0. And then 2 times 2 is 4. 4 minus 1 is negative 1. 4 minus 5 is negative 1, sorry. All right. And now we'll divide both rows by 2. And we get 1, 0, negative 1/2, 0, and 0, 1, positive 1/2, 0, and 0, 0, 0, 0. So that says that x minus 1/2 z is equal to 0, and y plus 1/2 z is equal to 0. And so if we put a parameter on that, that means that x is equal to positive 1/2 t, y is equal to negative 1/2 t, and z is equal to t. All right, so let's just pick a value for t. I'm going to let t be 2, so I've got some, so I don't have fractions here. So if t is equal to 2, then x is going to be 1, y is going to be negative 1, and z is going to be 2. So let's check this out. I'm going to weight this vector by 1. this vector by -1, and this vector by 2. And let's see if those add up to 0. So 1 times 1 is 1, minus 5, because we're making this by -1, plus 4. So 1 minus 5 plus 4 is 0. 4 plus -4 and 0 is cancels. And 2 times 2 is 4. -4 and +4 is 0. And the bottom row, this is 0. Multiplied by -1, this will be -2. Multiplied by 2, and this will be +2. -2 and +2 will be 0. And so now not only do we know that there's more than one linear combination, we actually know that there's a specific one now. The first column, 1, -4, 0. And the negative of the second column, so -5, 0, 2. And 2 times the last column, 2 times 2, 2, 1. That adds up to 0. And I want to use this fact in the next example, that this particular linear combination cancels everything out and adds up to 0. My weights are 1 and -1 and 2. All right. So what we're saying is that every vector now is a linear combination more than one way. In this example, we have the same vectors that we had before. And this is a linear combination that doesn't add up to 0. It adds up to 5, -10, 1. And so we want to quickly find another linear combination of the vectors that add up to 5, -10, 1. So we can slowly do this by row reducing and finding the free variable and parameterizing the system and everything like that. But if we want to do this quickly, we know that this combination weight the first vector by 1, the second vector by -1, and the third vector by 2. That combination adds up to 0. We already know that. If I add these together, 2 of these vectors plus 1 more of these vectors is now 3 times 1, -4, 0. 1 of these vectors and -1 of these vectors, these cancel. And I get 0 times 5, 0, 2. And then -1 of these vectors and 2 of these vectors adds up to just 1 of these vectors. And this plus 0 is just the original vector, 5, -10, 1. Oh, let's see how that works. Does that check? 3 plus 0 plus 2 is 5. -12 plus 0 plus 2 is -10. And 0 plus 0 plus 1 is 1. So that does check. So what we've seen here, what we've demonstrated here, is that as soon as we know that 0 has an alternate solution, as soon as we know that this combination is possible, then I can add that combination to any other vector, and now that vector has 2 solutions, the original solution plus the solution we got by adding 0 to it. And so what we've demonstrated is this theorem that was on the previous slide. I'm backing up. That if a set of vectors is linear dependent, then the definition just says that 0 has to be a combination more than one way. But in fact, every vector is a linear combination more than one way. We only have to test for 0, but it actually works for every vector. All right. So now let's move forward. If a set of vectors is linearly dependent, then at least one vector in a set is a linear combination of the other vectors in a set. That within that set that's linearly dependent is hiding a linear combination. So let's try this example. We want to show that this set of vectors is linearly dependent. That is, one of the vectors in the set is a linear combination of the other vectors. And I need some room to work, so I'm going to rearrange this slide. Boom. Let's look at this set of vectors. I'm going to row reduce this now. 1, 4, 1, negative 2, 2, 0, 8, 2, 2, 6, negative 1, 5. I'm going to augment it with zeros, but again, augmenting with zeros is not necessary because we've already seen that in a linearly dependent set, not only does 0 exist as multiple linear combinations, but any vector exists as multiple linear combinations. But I'm going to go ahead and use 0 for this example. All right. So I'm going to get rid of this 4. So I'm going to take row 2 minus 4 times row 1. 4 minus 4 is going to give me a 0. Let me go ahead and copy the top row. 2 plus 8 is 10. 2 minus 32 is negative 30. Negative 1 minus 24 is negative 25. And 0 minus 0 is 0. All right. Now we're going to get rid of this 1. We'll take row 3 minus row 1. Zero, 10, negative 30, negative 25, and 0. 1 minus 1 is 0. 0 minus negative 2 is 2. 2 minus 8 is negative 6. And 5 minus 6 is negative 1. All right. We need to get rid of this 2 now. So I'm going to take 5 times row 3 minus row 2. So I have 10 minus 10 to cancel. 0, 10, negative 30, negative 25, and 0. 0, 10 minus 10 is 0. Negative 30 minus negative 30 is also 0. Negative 5 minus negative 25 is positive 20 and 0. And so my leading entries are here. But we have a free column. Reduced echelon form helps to isolate the free column. So I'm going to use reduced echelon form here and do some more work now. So I'm going to take row 3, divide it by 20. Divided by 20, that's now a 1. And then clear out the rest of this column. Row 1 minus 6 row 3, and row 2 plus 25 row 3. And we get 1, negative 2, 8, 0, 0. 6 minus 6 is 0. And 0, 10, negative 30, 0, 0. And 0, 0, 0, 1, 0. All right. This leading entry is now in reduced echelon form. We want to work backwards to this leading entry. Change this 10 to a 1. So we're going to take row 2 divided by 10. So that's going to be 1, negative 2, 8, 0, 0, 0, 1, negative 3, 0, 0, 0, 0, 0, 1, 0. Oh, and finally, we're going to get rid of this negative 2. Row 1 plus 2 times row 2. 1. Negative 2 and 2 is 0. 8 minus 6 is 2. 0 and 0 and 0. All right. So, all right. So if we call the variables, since we have 4 variables, if we call them w, x, y, and z, these equations say that w plus 2y is equal to 0, and x minus 3y is equal to 0, and z is equal to 0, but we don't have an equation for y, so we're going to change y to t, and that gives us w is equal to negative 2t, x is equal to 3t, y is equal to t, and z is equal to still 0. All right. So we now have a linear combination that adds up to 0. What we have is that negative 2, so if I let t be 1, w is negative 2, x is equal to 3, y is equal to 1, and z is equal to 0. Excuse me, sorry about that. All right. So negative 2 times 141 plus 3 times negative 220 plus 1 times y plus 822 plus 0 times z. I'm not going to write that, adds up to the 0, 0, 0 combination. We can check that that works. I'm not going to take the time to do that, but it does check. And I'm going to take this vector and put it all by itself. I'm going to move everything to the other side. Because, so negative 2 becomes positive 2. And 3 becomes negative 3. That's a 4, 0. All right. And now this is a linear combination. This vector here, 8, 2, 2, is a combination that we get if we weight this vector by 2 and this vector by negative 3. And so this vector is a vector that's in a set, and it's a linear combination of these vectors, and they're just other vectors that are inside the set. And the theorem that we saw on the slide before this one says this always happens. If we have a linearly dependent set, then that set is containing a linear combination somewhere inside that set. One of the vectors is already a linear combination. So that's another way of testing for linear dependence. All right. Not necessarily fast way. We've seen a lot of work here to get to this result. But it's another fact about linear dependence. So what do we know so far? If a set is linearly dependent, 0 is a linear combination in more than one way. In fact, everything that's a linear combination can be done in more than one way. And the set of vectors is concealing a linear combination inside the set. All right. Let's move on. So we've already seen this definition. This is just a complementary definition. We say that a set of vectors is linearly independent if the zero vector can only be done in only one way. So dependent means many ways, independent means just one way. And now we have some theorems here, and I'm going to turn myself off so we can, see those theorems. The columns of a matrix are linearly independent if and only if every column contains a pivot position or a leading entry. Same thing. That is, in order to be linearly independent, there needs to be no free variables when I augment with 0. In order for there to be no free variables, this column has to have a leading entry, and this column has to have a leading entry, and this column has to have a leading entry, and this column has to have a leading entry. And so every column has to have a leading entry because we don't want free variables. Free variables gives you more than one way to solve a problem. Independence is what tells me there's only one way. And theorem 16 says that if I have a set of vectors that's in Rn and we have more than n vectors, if I have more rows or more columns than I have rows. So say I have 3 rows and 5 columns. So these are vectors in R3, but I have more than 3 vectors. Well, then there's no way that I can have a leading entry in every column because I run out of room for the leading entries. And therefore, the set must be linearly dependent. There must be a free variable if I have too many columns. I don't even need to row reduce. I can look at that and they say, well, it's a 3x5 matrix. There are too many columns, and so it has to be linearly dependent. On a test, you could save yourself a whole lot of time if you recognize that the shape of the matrix is enough to tell you that problem. So before I go to the next slide, I'm going to go back to the previous slide, actually 2 slides back. And because this matrix right here had 4 columns but only 3 rows, that was enough to guarantee that there was going to be a free column in there somewhere. That is because there's no way I can have a leading entry in all 4 columns in a matrix like that. And so even without doing any of this row reduction, I could have gone ahead and told you that the set was linearly dependent. I can tell that just by looking. And now you can too. So any set of vectors that is wider than it is tall has to be a linearly dependent set. All right, we have seen this definition before. I'm just reminding you. So we've seen this before. The system of vector equations ax equals b is homogeneous if b is equal to 0. And this is an example of a homogeneous system of equations. All the constant terms are 0. That means we're always guaranteed to have a trivial solution. When x is equal to 0 and y is equal to 0. We call that the trivial solution because I don't even have to row reduce to know that plugging in 0 for x and plugging in 0 for y is going to give me 0. That's just a way that 0 behaves. There is also a non-trivial solution. X equals 9 and y is equal to 6. No, there's not a non-trivial solution. Never mind, I lied. Um, there is not a non-trivial solution to this system. I thought there was, but I can't read. If there's a non-trivial solution, then it has to be a non-zero solution, but there isn't one here. Okay. Oh, so we have this theorem. It's a long one. Let me spend some time sort of piecing it out here. We have a set of vectors, and we have this matrix that has these vectors in these columns. Then all of these statements mean the same thing. This is what it means for the statements to be equivalent. One way of saying this is that S is a linearly dependent set. One way of saying this is that at least one vector in the set is a linear combination of the others. That's what we said a little while ago, that within the set, there's already a linear combination in the set. Another way of saying this idea is that the echelon form of A has a free column. Another way of saying this information is saying that if we have a homogeneous equation, it has an infinite solutions because we have a free variable, and free variables mean that there's an infinite number of solutions. And another way of saying this idea is that the equation, the linear combination 0, has a solution in which at least one of these weights is non-zero. In other words, it has a non-trivial linear combination that adds up to 0, because it's just any of these non-trivial solutions from number 4 we can use in problem 5 or part 5. All of these are just different languages for meaning the same concept. Okay. All right. So we're done. Let me just summarize what we've covered over the past couple of days. Spanning Rn means it's possible to build every vector in Rn as a linear combination. All we're saying is it's possible. We're not saying whether it can be done in one way or more than one way. We just know that it's at least possible. The test for spanning is if the echelon form of A has a pivot position in every row. If S contains too few vectors, if there's not enough vectors, then we cannot span Rn because we run out of vectors before we run out of rows. So if the set is too skinny, if the set doesn't have enough vectors, then spanning is not possible. We say the set is linearly independent if it is impossible to build any vector in more than one way. So that now we know that our solutions are unique because there's no other way to do this. That means there's no free variables, and therefore the matrix A has a pivot position in every column. So that contrasts with this. And in order to have a pivot position in every column, I can't have too many columns. If I have more than n vectors, then the set cannot be linearly independent. So a set that's too skinny can't span. A set that's too wide can't be linearly independent. In chapter 3, we're going to look at square matrices where everything is the right size, but for right now, we're not there yet. And so our sets might be too wide or too skinny to have this information. So this summary just has all the contrasts between the difference between spanning and linear independence. And I hope that's helpful. But we're done for today. You take care of yourselves, and I will see you next time.